My name is Onolapo Abayomi Samson. The topic that we are going to discuss today is sound waves. First, the introduction. Can you just imagine how the entire world would be without sound from animals, from human, vehicles, and so on? Sound is a wave that travels across a media. The media could be a solid, it could be liquid, it could be a gas, and its speed depends on the elasticity, that is, the stiffness and the density of the medium. Because of this, a study requires a systematic process. Recall, we earlier classified waves as mechanical, electromagnetic, transverse, and longitudinal. In this particular video, we will examine sound waves as a typical example of longitudinal waves. This will help you to understand how it travels in various media and why its speed varies in different media. Now the learning outcomes. By the end of this presentation, you will be able to define sound waves, state at least 4 sources of sound, describe the production and transmission of sound. Then finally, you will be able to solve simple numerical problems on sound waves. Now the nature of sound waves. Sound waves are waves that travel across an elastic medium from a vibrating body to a listener. So for you to hear the sound of a particular object, there are two things. The first thing is that there must be a source of sound, that is, what will produce or what will make that sound. Then there must be someone who is an observer that is going to listen to or hear the sound. Sound wave belongs to a class of waves known as longitudinal waves, whose direction is parallel to the direction of travel of that wave. Now look at the diagram in front of me here. Now you have a man standing and a dog barking at him. Now the dog serves as the source of sound and the man is the observer. Now the sound waves from the dog is going to travel through ear, and the man will be able to observe or listen to it. Likewise, you can see two people making telephone conversation. Now the person that is speaking on the phone is the source, while the person listening to him is the observer. So all these are demonstrating or telling us that sound as a wave requires a material medium for propagation. The material medium could be a solid, it could be a liquid, likewise it could be a gas. Now the sources of sound waves. We have divided the sources of sound waves into two. The first one, natural sources. For example, waves from animals, from wind, from flowing streams, from volcanoes, avalanches, and so on. Likewise, we have artificial sources. For example, waves from airplanes, helicopters, road vehicles, trains, explosions, vibrating tuning fork, blown whistle, city traffic, soft whisper, vibration of a drum skin, and so on and so forth. Now I want to talk about the picture beside the sources here. You can see from the picture that sound waves are longitudinal waves. Now the major thing that we are expected to know there is that no sound can propagate in vacuum. There must be a source that will produce that sound. We can see a siren with red cover at the middle making a sound, and the sound is propagating through air, while someone beside the siren is listening or observing the sound. Now, sound waves, how are they transmitted? That's what we want to discuss here. The mere vibration of a source of sound is not by itself sufficient to produce sensation of sound. There must be a material medium. So when a source of sound is just vibrating, although it will produce sound, but it's not enough or sufficient to produce a sensation of sound. There must be a material medium through which that sound waves is going to travel or propagate so that we can observe it clearly. So a material medium is essential to transmit the vibration to the ear because sound cannot propagate through vacuum. And when you look at the figure beside the transmission of sound waves here, we have a string. Now you can see the arrow pointing from left to right underneath. That represents the direction of propagation of that wave, and we can see along that string some regions are spaced out. These spaced out regions, we call them rarefaction, while some regions are compressed, we call them compression. Now compression and rarefaction, they are peculiar to sound. Now I have solutions to about two numerical problems here. The first one, it says for sound waves with a speed of 344 meters per second and frequency of 20 Hz and 20 kHz. In each case, we are to determine the wavelength of each of these sound waves. Now, from the simple formula that we have learned for calculating the wavelength of waves earlier, wavelength is equal to wave velocity divided by frequency. For the first case, 344 divided by 20, the wavelength happens to be 17 meters. The second case, 344 divided by 20,000. Now 20 kilohertz, we have to convert it back to hertz to give us 20,000. And by the time we make that calculation, the wavelength comes out to be 0.017 meters. Now for the second case, a sound wave has a speed of 344 and the wavelength of 0.5. What is the frequency of the wave? Now from that simple relation, we make frequency the subject formula. That is the speed divided by the wavelength. 344 divided by 0.5. That's going to give us 688 Hz. So to solve simple numerical problems on sound waves, all we need to know is this simple relation. The formula that relates the wavelength, the wave frequency, and the wave velocity or wave speed. This is going to go a long way to assist us to solve or to demystify any numerical problem as regards to sound. In the next presentation, I will be discussing the characteristics of sound waves with you. I most sincerely thank you for your time and for your attention. See you next class. Bye.